right, welcome back, team. In this episode, we are going to discuss solving logarithmic equations. If you need help with solving exponential equations, please seek that video on the Fostering Mathletes channel or the Google Classroom of our class. So let's consider these two examples. Number one, log base 3 of x minus 2 equals log base 3 of 4x plus 1. And number two, log base 3 of 6m minus 1 equals 2. We talked about with logarithm or anything that says solve, right? If I'm saying solve an equation, I want to determine the value of whatever the variable given is. So on number one, at the end, my goal is I should see x equals something. I want to determine what's the value of x. And on number two, I should see m equals something. There are two different cases in front of us. In number one, we see the case of logs on both sides with the same basis. And number two, we see the case of log only on one side, and we'll determine how to solve both. Beginning with number one, it brings us to the key idea that we talked about in class, this property of equality of logarithmic equations. And the key idea is written down here at the bottom. It goes as such: if log base b of x equals log base b of y, then x and y must be equal to each other. If log base b of x equals log base b of y, x and y must be equal to each other. So if I think about, hey, my base on the left side is b, and my base on the right side is also the same number b. Because my bases are the same, my arguments must be equal as well, okay? So these things inside the log must be equal as well. Same base, equal arguments. Again, same base, equal arguments. Knowing that, I can use the arguments to solve for the variable I want. So bringing us back to number one, we have log base 3. The base on the left side is 3. That's my b. Of x minus 2 equals log base 3, again, on the right side of 4x plus 1. Because 3 equals 3, and I have the same base on both sides, according to this property of equality, whatever's inside x minus 2 and 4x plus 1, these must be equivalent as well. Whatever's inside my log or inside the parentheses here, they must be equal as well. Okay? Again, because the base on both sides is 3, the inside of the parentheses must be equal or the same as well. Same base, equal arguments. So when I'm ready to equate these, I just need to write them down. Bring them down here. X minus 2 equals 4x plus 1. And I use my inverse properties to solve for x. I'm going to subtract 1x from both sides. There's a 1 in front of this x, so I know there's only 1 here, and it's positive. The opposite of addition or positive is a negative. So I'm subtracting 1 from both sides of this equation. It's going to cancel on the left side. And on the right side, I'm going to be left with 3x plus 1 equals negative 2. The next inverse operation to tackle is to move the numbers over to one side. So I want to get this positive 1, this adding of 1, over to the left side. If it's adding, I know the inverse of addition is subtraction, so I'm going to subtract 1 from both sides. That leaves us with negative 3 equals 3x. And then again, how I would read this statement mathematically is negative 3 equals 3 times x. Well, that times tells me multiplication is happening inside. To undo multiplication, we divide both sides by 3. That leaves us with our final answer, x's alone. Negative 3, a negative number, divided by positive 3, a positive number, will still give me negative 1. And that is our answer to number 1. X equals negative 1. We have solved this equation. If the bases are the same, that means whatever is inside the log is the same. Here, they both happen to be inside the parentheses, We equated x minus 2 and 4x plus 1, then used inverse operations to solve for x. Let's tackle number 2. I don't see a log on both sides, so I can't use the key idea written down here at the bottom. This key idea can only be used if there's a log or a natural log on both sides of the equation. I don't see a log on the right side on number 2. But I do know that in order to find the argument, I can change this to its inverse form of an exponential equation. In doing so, the argument will be exposed, and then I can try to find m and get it alone. So let's take this logarithm and change it to exponential form, all right? First, I'm going to identify all parts of my equation, starting with my base. Somehow I want this now to look like b to the x equals y. My base raised to my exponent equals my argument. I know my base here is 3, just labeling parts. I know my argument here, base. My argument here is 6m minus 1, and I know my exponent is 2. Okay? So because I want to change it to its form, I'm going to use all of these to change into the exponential form and rewrite this logarithmic equation. I should see 3 squared raised to the power of 2 equals 6m minus 1. Because my base is 3, my exponent was 2, and 6m minus 1 is my argument. From here, it's our job to simplify and use inverse operations to evaluate what does m equal. I know here to simplify 3 squared is 9. So 9 equals 6m minus 1. Then using inverse operations, I'm going to tackle that negative 1 first. I know the opposite of subtraction or negativity is positive. We're adding 1 to both sides to get rid of it. Cancels on the right side. I'm left with 10 equals 6m. 6m is multiplication happening. The opposite of multiplication is division. Divide by 6 on both sides. This cancels out. So after canceling the 6 and isolating m as a variable, it's now alone, and I know that it equals 10 divided by 6. Or simplified, that is also 5/3. So in this example, there's a big difference from number 1. On number 1, we started with a log on both sides. We used the knowledge of same base, means the arguments are equal to each other, and we brought them down to equal each other and used inverse operations to get x equals negative 1. In number 2, there was only a log on one side, so we used inverse properties to change the whole equation into exponential form. 3 squared equals 6m minus 1. And in doing so, we simplified where we could. 3 squared equaled 9. And we used inverse operations again to isolate the variable of m and get its value. Here we have solved 2 cases of logarithmic equations. Thank you for joining.